So we'll start now. I guess I'm audible. Thanks all of for confirming. Okay. So this is the third class. Started the recording. We are studying antennas and radiating systems. If the audio is not clear, you can please let me know. Um, okay. So we have been with this is the third class, and we have looked at the introduction, the radiation of fields in elemental electric and magnetic dipoles. In the last class we looked at the antenna patterns and antenna parameters. This class we will study thin linear antennas, discuss the half-wave dipole and the effective antenna length. This is the book that we are following. We are going line by line through this book. If you need in-depth details, as I've said, you can refer to Antenna Theory by C.A. Balanis. And so in the previous class, we had covered antenna patterns and antenna parameters. Maybe we'll I'll just go over these things, and if you have any questions, we can take them, or we can start with today's material. Okay, so maybe we can quickly look at things that we did. So we started with antenna patterns. Um, okay, there is a message that somebody is in the queue and they can. I'm not okay. Not sure why this issue keeps happening and people are not able to join. Okay, we'll try to get him in. Bear with me. Hi, Bhavna. Please bear with me. So there's someone in the group saying they are not able to join. I'll try to add them by some means. I'm not sure how things go. Um, Maybe through Outlook I can invite them. Okay. Okay. So I've sent them an email, the invite link. Let's hope that works. Meanwhile, we'll just go over the material from the last class and let's see if he's able to join. So we're looking at the parameters, the patterns and parameters. We looked at the radiation pattern for a Hertzian dipole, a realistic dipole. We looked at the polar plots, the rectangular coordinate plots. We discussed some more things in details, like the beam width, the side lobe levels, the directivity, and yeah. So basically, we quantified them using expressions. Yeah. So in the yeah. So in the last example that we did in the previous class, we concluded that a Hudson dipole, that is a smaller dipole, has a lower radiation efficiency, but we cannot surely say that it will be good for larger ones. But we did find out that for a smaller dipole, it's not as good. So in this class, we'll start with thin linear antennas. I don't see that he has joined yet. Anyways, let's continue. If that person faces issues, they're telling me that when the meeting starts, oh, okay, one question to the attendees. Uh, did anyone join the meeting link without signing in, like without like just directly, or did everybody had to sign in, like do a login thing with Teams?
Mm.
Yes, Aishwarya.
Am I typing? Uh, where is that? Where is that unmute button? Shift. So I joined using that link provided by. Your link is not working, but there's one.
On the email
Not
or
from the email, but there is one person who has shared that NS link. There's one person called NS. He has shared that link. I've joined using that.
okay, where's that link? Why is I'm not sure why
I'll
this
share that link
bursting.
again.
Okay, please do that on the WhatsApp
Yeah, yeah,
group.
yeah, yeah. Yeah.
This is this used to work for all other meetings, but I'm not sure why this happening. Okay, let me use the link which that person has shared. Um, what happens if I do that? Continue. Okay, I just use the one of the links which the, was shared by Ashwarya on the group, but it works. I did it in incognito by just entering my name. It works for me in without signing in as well. I'm not sure. Let me check if Sarla here. She said that she couldn't join. Okay, we'll continue with the class. Let's hope this works out for everybody else. I'm like, not sure. Like I've tried it in the incognito as well. It works for me. So somebody said that they finally got in. I'm guessing this is true for everybody else. So everybody joining now, we were just discussing stuff from the last class, and we'll begin with the new material from now. So you haven't missed anything. Okay, we'll start at the point now. So we're starting with thin linear antennas and half dipole and the effective length things now. Um, I'll just again confirm once I'm still audible, right? And the screen is visible to everybody. Okay, maybe Ashwarya, you can confirm.
Yes, sir.
Okay, yeah, thanks. So we'll proceed then. Uh, so starting with thin linear antennas. In the previous class, in the last example, we saw that we saw that short dipole antenna is not good radiator of electromagnetic power because of its low radiation resistance and low radiation resistance and low efficiency. You can refer to the example that we did in the last class. Over there, we derived this thing. And in this class, we'll look at thin linear antennas and linear dipole antenna. And what is that? It is a center-fed thin straight antenna having a length comparable to the wavelength. So For example, if you are looking at this, so this particular this length of this antenna will be comparable to one wavelength of, if this is equal to, this is somewhere near lambda. So in general terminology, if it is less than lambda by 10, it is believed to be small, like the much smaller the antenna. So that qualifies somewhere around the Hertzian dipole, or usually referred to as lambda by 50 is somewhat we use for Hertzian dipole. So this is a small antenna, and this is lambda by 50 is what we call a usual Hertzian antenna, Hertzian dipole antenna. And over here we look at half dipoles, and then dipoles. So dipole will be equal to lambda, half dipole will be lambda by 2 and stuff. So its length. So in this class, we'll look at antennas whose length are comparable to the wavelength. When we say comparable, it is greater than lambda by 10. It does not really mean that it should be very close to lambda. It just says that it is significant enough that we cannot ignore its like the length of the antenna. And in this case, so when we were using Hertzian dipoles and stuff, we could easily assume that the current through the antenna was same. So, but in a more realistic antenna, or in a dipole whose length is comparable to the wavelength, the current distribution will not be like constant throughout the antenna. It will vary over the length. And this null this current distribution is actually, we'll see in the next few slides, it's very complicated, and using that is also using that and deriving results is difficult. So what we do is we assume a certain kind of current distribution, and then we proceed with the derivations. And even then, it's still difficult. And what we do is we do more approximations to get a result. But whatever results we end up with is good enough for like our work. So if the current distribution along the antenna is known, we can find its radiation field by integrating over the entire length of the antenna radiation field due to its elemental dipole. So what the sentence means is that in the previous class, what we did was we took a very small antenna, and by using the derivations and stuff, we got the electric field and the magnetic field at the distance. Now, what we can do is assume we know for this small length, this is the electric field. We can say this length as dl length, and this dl length causes dE and dH electric field, electric and magnetic fields. We can integrate over this dl length, and which implies we'll get the full length of the dipole, and similarly we can integrate this electric field to get the effect of this the to the and the full antenna. So we're taking the small length section of, and due to the section, what is the electric field at this distance over here? And then again, due to this next section will have some effect of the, let's say this is E1, will have some E2 at the same point. I hope everybody remembers the principle of superposition. So this is basically the simple principle of superposition. We're considering multiple dipoles arranged in this fashion to form one big dipole, and the effect of each dipole at a certain distance will cause some electric fields, and we'll just add those effects to get the final total electric field from this entire structure. The determination of exact current distribution on such a seemingly simple geometrical configuration, that is a straight wire of finite radius, is however very difficult. As I said, the uh, the knowledge of how the current is distributed along this dipole is like finding that out is very difficult. And even with that, if we have that relationship, the boundary value problems will be very difficult at the edges. The boundaries wherever we have, that will create issues. So the important things are the current must be zero at the ends of the wire. So like, for example, if we are taking this distribution, later we'll see we're taking this some sinusoidal distribution. So we have to ensure that the at the end the current is zero, because this is we cannot have a high value of uh, uh, over here, and we have to make sure that tangential electric fields are zero over here, because this is a conductor, right? And so this implies we'll have some boundary conditions at the end of the wires. So essentially, what we're trying to say is that we have to do a lot of approximations. Even with the approximations, the integral equations will become very complex. So you can read the text in the book. Essentially, it all says that we have to do approximations, and even with approximations, it's still difficult. So unfortunately, an exact solution of integral equation does not exist, even if we have the full knowledge. So various approximate solutions have been tried. Uh, and this is being said for if we have found out the exact current distribution or an approximate current distribution. So for to simplify our lives, we will assume a simple current distribution, and we'll get some results, and those will be good enough for our work. So this is an advantage written over here with high-speed digital computers that we have right now. The approximate solutions have become much easier to solve now. We have numerical methods to find out to evaluate those integrals. And okay, one definition is over here, that the ratio of the voltage and current at the feed point is called the input impedance. So this is the feed point over here, and the ratio of what the voltage is over here and the current is over here will give us the input impedance of the antenna. I hope I've written the formula correct. Yeah. So over here, but again, finding this out is also a task. Okay. So since the those derivations are very complex, we won't get into the complex derivations. We'll do a simpler derivation. Uh, so for our purposes, the knowledge of exact current distribution on the linear antenna is not of prime importance. So what this means is it could be a very uh, different function, but using a mathematical model for this function might be very difficult. So what we do is we take an approximate function, which is much easier. So just to give an analogy, for example, if there is a function which looks like this, and you have to do an integration, and writing this will involve, even if you are able to write this, will have sine x, sine y, cos x, cos y. It will be summation, and there will be powers of trigonometric terms. So this is very difficult to, for example, if you are performing some maths with this. But what you see is this looks very similar to to a simple sinusoidal function. So what we can do is we'll just take the sinusoidal function and integrate and look at the results, and hope that it does not deviate much from the uh, expected results. So that is what we are doing over here. So a good estimate will give us considerable useful information on the radiation characteristics. And we will take it as sinusoidal. We'll see that now. So we assume a sinusoidal current distribution on a very thin straight dipole. So this is on the line over here. This is the sinusoidal distribution uh, on a straight dipole, and such current distribution constitutes of kind of standing wave over the dipole and represents a good approximation. So not will not get into details, but with literature, it has been observed that over the dipole, what we get is a standing wave configuration over here. So it is usually like something like this, some form of current distribution which forms like this. So it forms a standing wave over the dipoles with zero field at the zero current at the corners. And since the dipole is center driven, the current on the two halves of the dipole are symmetrical. So as seen over here, we are feeding it from the center. So whatever, so we are giving some voltages and currents over here. So both the sides of the dipole will have a similar current. For example, if it looks like, if we're feeding it over here, it will either look like this, or it can either look like this, or some form of fashion. So basically, it will be symmetric along this line. And so we can, with this knowledge, we can write the current phasors as this expression. So this is sine beta h minus z. So z is the in this direction we are moving. This is z, and h is the total length. And essentially, this particular function that you have seen, it is drawn over here. So we have defined a current distribution over the dipole, and with this we'll proceed with our results. So maybe I'll pause over here if you want to go through like read this function, how this looks like. Okay, we'll proceed then. So we have decided a current distribution over the dipole antenna. From the previous classes, you must remember how we found out the electric and magnetic field for a dipole, an elemental dipole in the far field. So this the magnetic and electric field expressions in the far field for a elemental dipole. And so we are only interested in the far field zone. So hence we're using these expressions for the far field. The far field contribution from differential current element IDZ. So this is for the elemental dipole, and if we have to integrate, if we have to find out for the electric field due to the entire structure, and we are taking the elemental section of over here. So for this particular section, the electric field would look something like this. So this is the exact, and this is the same expression in 1119b. It's just that we are writing it in the differential form. So we have dE over here, and this IDZ over here. Okay, so this dl becomes dz, and this E becomes dE. Now R hyphen in this expression is slightly different from the R uh, from the previous derivation. So in the previous derivation, when we had the elemental dipole, the R was this length, and we assumed that this particular length is very small, so this R was fine for the entire distance. But now this particular R hyphen R dash is considered like at a much larger distance, and hence this might create problems. So we have to approximate it with approximate it carefully. So this R hyphen can has to be now written in terms of R and Z. Okay, so how we do that is, so you will have to go back to the high school geometry. For example, if this was the antenna, I'm sorry, this was a triangle, and this was the theta angle, and let's say this is Z. One side is Z, and the other side is R, and the third side is R dash. Now, if we have to find out r dash and we have to write it in terms of r, theta, and z, this is something we'll end up with root over r square plus z square minus 2 rz cos theta. So this is the expression for uh, the unknown side of a triangle. If we know the angle and the length of the adjacent arms, so this is what it look like. And so this is yeah. So it is usually it is r dash square is equals to r square plus z square minus 2 rz. Give me a second. Okay. Um, yeah, so you get it, right? This is 2 rz cos theta. So this is the expression, and now we need just the r. So we take a root on both the sides, and we end up with this whole thing power 1/2. Now using the binomial expansion, so there is quite a lot of steps from here to here. So what we have done is we have taken this r square outside this thing, so we get r 1 plus z square by r square minus 2 z by r cos theta whole power 1/2. Now we know that this particular r is much greater than h, which imply, and since this z is in moving its maximum value is h, so it implies r is much greater than z as well. So this particular term we can ignore. So we can ignore this, and by using binomial expansion, we uh, we will end up with something like this: r1 minus uh, half into this term 2z by r cos theta, and we are ignoring all the higher order terms because z by r will the powers of z by r it will be since r is much greater than z, it will be close towards zero, so we are approximating that. So canceling these twos will end up with multiplying this r with 1 we get r, and multiplying this r with z by r we get z cos theta. So this is how we define r dash in terms of r minus z cos theta. There's a question. Okay, there's a question from Hanuman. Why does r why does the cos theta term comes into the calculation? So we have to note that okay, there is this r dash is although it's in the far field, which will still we're starting with this line over here. For example, even if it is in the far field, um, this is something it would look like, right? This is r dash, this is r, and then this is z. So uh, this exactly isn't a right angle triangle. So hence we are taking it as a scale-in. So it would a further step would be if you just want to ignore this term, but that would actually have some effects on the results. So we instead of approximating a right angle triangle, we're taking a scale-in triangle, and it's still it's not very difficult to do this thing. So we're not approximating that as well. To answer your question, the cos theta term comes in because this is a scale-in triangle, as we're approximating it to a scale-in instead of a right angle triangle. Okay, so we'll proceed. So we have found out r hyphen in terms of r minus cos theta, and the approximation which you said will also come in later. So the magnitude difference between 1 by r and 1 by r dash and 1 by r is insignificant. So the magnitude wise, so these two is it's fairly like simple. Like it's not the r hyphen r in magnitude terms, it will be fine. But when using this in at the inside the integral, we cannot ignore this z minus cos theta terms because this will actually affect the phase uh, of the solution. So it will bring in effects. So we cannot ignore that. Okay. So so it must be retained in the phase term, which is the term which is inside the e power exponential things. So using the equations 51, 53, and 52. So let's see, we have the expression 51 over here, which gives the current distribution, 52, which gives the electric field expression. Uh, so we have r dash over here, r dash over here. So this r dash can be approximated as r because magnitude is not much affected. But this particular r dash has to be approximated as r minus z cos theta. A simpler way could have also been in this thing is this r dash and this r, they are they kind of equal, and this theta is this theta angle. So if you know this z, if you know this theta, this particular length over here is z cos theta, and so your r dash would be equals to, okay, no, we your r dash would be r minus, okay. So okay, so I thought of this right now, but I don't think this works. So better we do this way, how the textbook does it. Just ignore this thing which we're trying to do. Anyways, so we have the r dash expression. We can put this r dash expression inside the this term over here, over in these two places, and the current distribution over here as well. And upon doing that, we will end up with this big integral over here. Okay. So this integral, this I term has been replaced by this expression over here, Im sine beta minus beta sine beta h minus mod of z. So Im was constant, which is inside, sine beta h minus z is inside the integral, and then we have replaced r dash with r minus z cos theta, which so which implies, so e power r minus z cos theta can be written as e power r and e power minus z cos theta. So this is the z cos theta term over here and e power r term over here, and this j beta is multiplied to both the terms over here. I Yeah. Um, maybe I'll pause over here for you to go through the slides. Give me a couple of minutes. I'll be back. Maybe meanwhile you can look at the derivation that we did. If you want to work it out on a paper, that as well. Okay. So I hope everybody got time to go through the steps. If there are no questions, we'll proceed with the derivation. So up till now we defined the current, then we defined the wrote down the expression for elemental dipole, and where now we integrated it to get the expression for the electric field. Okay, so in the previous slide, we have got the expression for the electric field, but we are still left with this integral over here. Okay. Now the integrand in this over here is a product of an even function of z. So this particular term sine beta h minus z, this is an even function. An even function is something which is symmetric on the y-axis. It could be a function looking like this, or I hope I'm doing it correctly, or something which looks like this. That is, so you get the ideas, which is like symmetric uh, along the axis. Um, and this is an even function of sine beta term and this exponential term over here. And now this e power j beta minus cos z, this is the Euler form, and it can be written in this Cartesian form like this. So yeah, so this argument comes inside the cos and sine functions. Now in this term, sine beta cos theta, this particular term, this is an odd function. Okay, so this term, this is a simple sinusoidal function. So this is looks like something like this. So this is an odd function, and now we are integrating it between the symmetrical limits of h and minus h. So this integration is from minus h to h. So this means we're integrating a function um, from minus h to h, and so we know that if it is an odd function like this area will negate this area, and we end up with 0. So this particular basically this, and we also know that even function, if it is multiplied by odd function, it ends up an odd function. Okay, so this essentially this term multiplied by this term will end up an odd function, and the integral of odd function is 0. And this even function multiplied by an even function ends up an even function. So we will get some finite value. So this particular sine beta h minus z and cos beta z cos theta, this is the only product which does not vanish. So we only need to integrate this, and if we integrate this, see, we are integrating this from 0 to h. And notice we had 4r over here, which becomes 2r, because an even function's integral, for example, if we are integrating a cos or something, an even function, so this area and this area, they are same. So instead of integrating through the entire space, we can only integrate it in the positive half and multiply it by 2, and we'll get the equivalent integral. So integrating from 0 to h, and why we do this is because one of the limits becomes 0, which is much simpler to put inside a function. So essentially, we are simplifying this electric field, and we have got this function over here, and this integral is now we have written it as in terms of f theta, and this f theta is so upon integration you will end up with a function which looks like this, and we have just written this it is in form of f theta. So electric field equals eta times magnetic field equals J60 into IM, which is the maximum current value upon the distance r, e power minus j beta r, all these are constant, and the only thing varying over here is the function, all the terms which are function of theta is written over here. So you have to notice we have written 60 over here, and the 60 has come because eta is 120 pi. We substituted that. This 2 pi and 125 cancels out to give us 60 im. So I'll again pause over here and let you read the text. Let me know if you don't, if you have confusion or if you don't follow it at any step. We can discuss that. Else we'll move forward. There was a question by Hanuman in Q&A. How to measure or calculate the impedance of a dipole? So it's pretty complex, and it's not like in this course we won't be covering the impedance of a dipole. We looked at the radiation resistance, which was part of this course. If you want to like study the impedance of a dipole, you'll have to go through texts. It's pretty complex, and not we won't be covering that. I'm sorry. We are like, it's that's whole another class will be needed with complex maths. I think you can refer to Balanis, and it's probably discussed in Balanis. I maybe I can share the textbook if you don't have that. Okay, so we'll proceed. Okay, we'll quickly summarize and then move to the next slides. So we had this dipole over here of certain length, which is comparable to lambda, and then we decided a current distribution on the dipole. We uh, we wrote down the electric field due to one of the elemental sections of the dipole, and then we wrote down the expression of r dash in terms of r, and then substituted that inside electric the differential electric field, and then integrated the entire thing to get the complete electric field. And inside this electric field, we have to solve this integral. We change the Euler form to the Cartesian form. This term becomes zero, and then we integrated these two terms. And upon doing that, we ended up with this function, this expression over here, this electric field looks like this, and this particular function is written in this form. And now this particular function is the E-plane pattern function of the linear dipole antenna. In the previous class also we were looking at E-plane pattern functions, and this expression is the E-plane pattern for the linear dipole antenna. So I'll again pause on this slide. We are summarizing what we have done so far in the slide. Okay, so we have looked at this quite a few times now. I hope everybody follows. So we have got the plane pattern function. Okay, So it describes from the previous class as well. This pattern function describes the radiation pattern and the variation of the normalized far field, the electric field with the angle theta. And this, if you look closely, this is a function of beta and h, which h is the length of the dipole. So if h changes, the pattern will change, and beta, which is 2 pi by lambda. So if the wavelength also changes, that is which is the excitation for different lambda values also this will change, and it will be different for different antenna lengths. And the pattern is however symmetrical with respect to theta equal to pi by 2. So this particular line over here, this is theta equal to pi by 2, and it will be symmetric on both the sides. So this is figure 16, where we are plotting the E-plane radiation patterns for center of the dipole antennas for different lengths. Um, so for h equal 2h by lambda, when this is half, so this is quarter dipole. Uh, okay, so this is this is a half dipole. Um, the radiation pattern looks like this. For a dipole, the pattern changes, but we still have the maximum radiation. Um, so the dipole has placed something like this. Okay, as seen in the figure, this is z-axis. So dipole is at the center, and we have radiation on both the side. And like this is, and so this is the cross section. So essentially, if you look from the top, it will be radiating like this, and if the dipole is pointing in the up direction. Okay. So this looks like a donut. This also looks like this, or in Indian context, it looks like a vada. And this is a flatter vada, and now this thing, if we, this it becomes 3 by 2. Um, this okay, so this is 3 by 2 lambda distance. Um, so this is now. This looks like a helical. This looks like two cones, if you can imagine. This is like cone, and then there is a disc and along the dipole. And this particular radiation pattern looks like two funnel shapes, if you are able to follow. Okay, so this is how the patterns change, and you can plot these by using MATLAB by changing the values for h and plotting and for different theta values. This beta h you can put right like this, and you can plot these radiation patterns. So we have done a general derivation for thin linear antennas. Now we'll move towards half dipoles. Maybe if there are questions, we can take them now, or we'll move to the next topic. So we have two more topics to cover: the dipole, half dipole, and the effective length. Okay, okay. So I think I was on mute. So we started a little late, so maybe we'll stretch after 5 as well. Let's see how much we can cover. We're starting with half wave dipole antennas. Its length is the length is given as 2h equals to lambda by 2. So if you remember in the figure, this was the dipole antenna's length was this was the h before, above the zero axis and h below the zero axis. So the total length was 2h, and now this 2h is equals to half wavelength, which is lambda by 2. Okay. So and we'll examine the properties of for a uh, half wave dipole in a greater detail, because this is one of the more popular antennas uh, uh, for the point of study and application as well. Okay. So for a half wave dipole, the this beta h can be written as this beta is 2 pi by lambda, and this multiplied by h, and then this is equals this h is equal. We wrote down that 2h is equals to lambda by 2, so this becomes pi by 2. I hope everybody followed that. Beta h is equals to beta is 2 pi by lambda, and h was 2h was lambda by 2, so h was lambda by 4, and upon doing some simple mathematics we end up with pi by 2. So now beta h is pi by 2. We can substitute that in the expression. Here we have the this was the pattern expression. In in place of beta h, we'll substitute pi by 2. So cos pi by 2 is 0, so that this vanishes, and sine pi by and we have sine theta, and this is cos pi by 2 cos theta. So this function has a maximum equal to unity at theta equal to 90. So if you substitute that directly, um, this cos theta will becomes this will become 0. So this entire function will become 0, and cos 0 is 1, and sine theta is sine 90 is also 1. So this its maximum value is 1, and this will have null set theta equal to 0 degree and 180 degree. So this is how the pattern would look like. So it's 1 at uh, 90 and 270, and 190 and 270, and we have nulls at 0 and 180. So this so where we can you can directly use MATLAB to plot this. The corresponding E-plane radiation pattern, which is sketched over here, and the far field expressions. So we had the expression for electric field. So we can substitute uh, over here beta h as pi by 2. This is this was the f theta, right? So we're substituting f theta over here. And similarly for h5 also, we got the expression for electric and magnetic fields. And now what we do is we're finding the power through the pointing vector as for half of E theta h5 conjugate. And for that, we will take the conjugate of h and multiply it with electric field. And this is what we end up with. This is so you can write these expressions and do the math yourself as well. This is just multiplication and writing. So we have got the pointing vector as 15 pi im square. Im is the maximum current, r is the distance, and then the square of the pattern function. Okay, so by using the pattern function for beta h equal to pi by 2, we got this pattern. We got the pattern function for a half wave dipole, uh, and then using the electric field expression and substituting this thing inside the pattern function, we got the expressions for electric and magnetic fields. And once we got them, we wrote down the pointing vector, and we are finding the average power. So that, and now this is the average power, and we can find the total power by integrating the average power across the surface and encapsulating the dipole. So So we do that by, so this is the solid angle thing, if you remember from previous class. So if we have a dipole over here, and if we have a surface around it, and we are doing integral in the spherical coordinate system, so this with r square sine theta d theta d phi is the uh, unit area on the surface, and then we have to integrate it over 0 to pi for theta, and 0 to 2 pi for phi. So we can do that. It's just tedious maths. And once we have done that, like, use MATLAB for it, maybe. So if we do that, we get the expression for total power in terms of the maximum current that is flowing, maximum current on the dipole antenna. So we've got the maximum power, and we can find out the radiation resistance by uh, this expression. Power is equals to, I think, I square R, and R can be written. So this is P. R is equals to, sorry, half I square R. So this is the average power. So R is equals to 2 pi by, sorry, 2P by I square. And upon doing that, so we have IM over here, and this is 2PR. PR we have substituted from here. So we end up with 73.1. So this is the expression for the radiation resistance. Maybe I'll pause over here if you want, like, for you to go through uh, the steps that we have done. We have found, we calculated the expression for electric field and magnetic field in the far field for a dipole antenna in the previous section, and then we also had the expression for the pattern function for the dipole antenna, and then we for the special case of half wave dipole, we uh, we found out beta h is equals to pi by 2. Substituted that into the pattern function, got the reduced pattern function for the half wave dipole, substituted the half pattern function for half wave dipole inside the electric field expression and magnetic field expression. So we got the electric field and magnetic field in the far field, and then use the expression for electric field and the magnetic field in the far field to get the Poynting vector, so average power from like, which is radiated from the antenna, integrated the average power to get the total radiated power. Once we had the total radiated power, we calculated the radiation resistance. So we went step by step through all the expressions. Although we are not doing all the, like, math, like writing the steps or solving the equations, we it is important that we know which steps comes next, because doing an integration of cos or sine is pretty straightforward. It's more important that you know what step to do next. As if there is any problem in the steps that we did, we can take the questions now or later, or you can write them in the chat. Um, okay, I'll pause now. I'll let you read the slide, and then we move. Okay, so there is a question: difference between the radiation resistance and the impedance. Okay, so when we started the class, we had defined the input impedance for the antenna, which is the, for example, this is the dipole and this is the feed. Input impedance is the ratio of voltage to the current at the feed. This is the input impedance. And in the previous class, we had defined the radiation resistance, which is an equivalent value for example, this particular this dipole has some current, and then this is radiating some power P. So by using this current and power, we can find out a fictitious resistance value, which gives us an idea of how much. So this is an antenna parameter which is defined. So this doesn't really exist as such. So this is a parameter. So radiation resistance gives you a quantified value of how much um, uh, power will be radiated. So so for example, if you are told this is the radiation resistance of this antenna, so what you can do is, and they tell you this is the amount of power that you want. So if you are given this much power you want, and you know that the radiation resistance of this antenna is this value, what you can do is calculate the amount of current that you need to feed inside the current you want to feed to the antenna, and so that you can achieve that amount of power. So this is the value of radiation resistance, the importance of radiation resistance. So the radiation resistance is a parameter of the antenna, which can be used to get the amount of power that you want based on the amount of current that you will give into the antenna. And input impedance is the term which is the ratio of voltage to current at the port. And this is used when you have to match the antenna to the rest of the circuit. So if there is an impedance mismatch, you have to make sure that you put in the current matching circuit. I hope that made sense, Hanuman. Do you have any follow-up questions? So Hanuman's questions are in Q&A, which is different from chat. So you can also post questions there as well. Um, so I'll wait for any other questions. Meanwhile, I'll write a quick answer on the Q&A. Okay. If there are no further questions, we'll proceed. So in the previous slide, we have done radiation resistance and the radiated power. the total radiated power. And now we'll look at the directivity. So the directivity of a half-wave dipole can be found out using the previous expressions that we have done. So let's look at 1135. This was the definition of the directivity. The maximum radiation intensity to the average radiation intensity, which is 4 pi u max by PR. So in the previous slide, we derived the PR value. Now we need to derive the Umax value, and from the expression for like yeah, we have to find out Umax. Now Umax U is R square up to P average, and we uh, the P average at 90° we have to take the value. So if you remember, the radiation pattern looked something like this, right? So the maximum value will be at over here, which is theta equals to 90°. So that's why we are taking the P average at 90°, um, and the P average expression in the previous slide is over here. So theta equal to 90°. This entire thing turns to 1. This is 1, and we have 15 I square m upon pi r square, and we are multiplying with r square, which is over here as well. So we end up with 15 upon pi I square m. So this is the U max, and and this is U max, and then we from the previous slide we have the expression for PR as well, which is over here. So substituting that, so this is 4 pi into 15 upon pi, um, which is 60, and then we have 36.54 in the denominator, and we end up with directivity as 1.64. And we saw in the previous classes that we usually write directivity in decibels or the logarithmic scale. So 10 log 10 of 1.64 is 2.15 dB, referring to an omnidirectional radiator. So this means so okay, so this means referring to an omnidirectional radiator is saying that this is 2.15 dB compared to an antenna which would radiate in all directions. But since this is radiating in a donut shape, so we have higher directivity along this plane. And we also write it as 2.15 dB I. So when we write this I, this refers to isotrope the isotropic, or yeah, so which is also like equivalent of saying with respect to an nominal relation radiator. So when we are writing this, we had also derived gain as well, right? So over there as well, so this term dB, this is also not an actual gain. This is with respect to an omnidirectional radiator. So for an omnidirectional radiator, we say that it is radiating it's that reference is as 0 dB, and with respect to that we have 2.15. So we are kind of getting as a fictitious gain over here of 2.15 dB, if you follow. Okay, so anyways, we had discussed directivity in detail in the previous class, and now we're just deriving those parameters for a half-wave dipole. So we have got the directivity equals to 2.15 dB. Now, the another term that we derived, like discussed in the previous class, was half power beam width. Now, to calculate half power beam width, we if you remember, so this would be this angle, right? So this over here, the power should be half as with respect to, if this is 1, this has to be 1 by root over 2, right? So equating to that, so we are taking the pattern function and equating it to 1 over root 2. And then if we solve this, we can solve this either numerically or graphically, and we get a beam width of 78 degrees. So this half power beam width is 78 degrees. uh, which is only slightly more different from a Hudson dipole. If you remember, for a Hudson dipole, um, it was okay. Yeah, for the Hudson dipole, it was 90 degrees, right? So this was much more like this, and this angle was 90 degree, and for this dipole, this is slightly more directive. So we have a smaller beam width. So so we have calculated. We started with the expression for current. Then from current, we wrote down the electric field, like for an elemental dipole, and then we calculated the complete electric field and the magnetic field. Then we wrote with respect to a pattern function, and then we chose a specific half-wave dipole as to which is equals to lambda by 2, and then using that we again we wrote down the expression for electric field, and then the magnetic field we wrote down the expression for average power using the Poynting vector. Then we calculated the total radiated power. From the total radiated power, we found out the radiation resistance. We also use the P average to wrote down to find out U max, and then we used U max and PR to get the value for directivity, and we also use the pattern function from the electric field and magnetic field to get the half power beam width. So this is essentially the gist of what we have done till now. I'll pause over here, and if for any further questions that you have, is there any? Okay, so Anumant had another question, which I missed. Radiation resistance is much closer to the impedance, 75 or 50 ohm. Okay, so this discussion is slightly different from what we'll be covering now. So radiation resistance is a parameter that we define for like if you want a certain amount of power, or so it's like one of the properties of the antenna, which relates towards the amount of power that will be related. So and this could be closer to the input impedance. It could be different from the input impedance. It's uh, it like as far as I know, it doesn't have to be same. uh, the question which you have asked is whether is it close to 75 or 50 ohm. The 75 or 50 ohm are the standard values for impedance, which is for the input impedance. So the input impedance is either 25 ohm, 50 ohm, or 75 ohm, and these values were chosen as the 50 ohm was chosen as a standard. So this is a different discussion altogether. But yeah, I'll say the 75 ohm or the 25 ohm, these two values were achieved due to better efficiency, better power transfer, or like there was another factor due to which either 75 or 25 where the values were one of those were maximum, and then as a trade-off, 50 ohm was chosen as the middle ground. So I think you can find this discussion on forums online. I'll also look it up and maybe share it in the group. I hope that answers. So radiation resistance need not be 75 or 50 ohm. It could be any other value. It is just a parameter that we are given in a data sheet of the antenna. so that we can find out how much like how to feed the antenna, how much power that it will radiate for a certain current value, or how much current that we should feed it to get a certain power value. And for that, the matching thing is 50 ohm or 75 ohm is chosen as a standard. And what we do is we try to make the antenna to get that particular impedance value. Any follow-up questions on that, Hanumanta? I'm not sure if I was able to uh, convey that like correctly. Maybe I can rephrase. Okay. Um, so we'll proceed with uh, the rest of the material. We'll quickly look at an example on the quarter length dipole over a quarter wave monopole over a conducting ground. So up till now we were looking at a half wave dipole, which had a feed over here, and then there is the other arm. So there could also be cases where we use a uh, so this is a message from Hanuman. The radiation resistance term is used in TX mode and RX mode. They use input impedance. Probably, I'm not sure, so I cannot answer this right now. Maybe I'll look it up, but maybe this sounds plausible. Okay, so this in this example, we are given a thin quarter wavelength vertical antenna, which is placed perfectly over a perfectly conducting ground. So this is PEC, and we have a quarter wavelength antenna, and there is feed on the one end. It is fed only on one end, and is excited by a sinusoidal source at its base. Find its radiation pattern, radiation resistance, and directivity. So up till now, we were dealing with an antenna which had feed at the center, and then it had two arms. Over here, one of the arms has been removed, and we are given a ground. So the problem is will can be easily simplified by using the image theory. So I hope everybody remembers, if we have a PEC and if we have dipoles, its image looks like this. Electrical dipole looks like this. Um, okay, maybe a step further. So if we have a small dipole is there's a positive charge, there's a negative charge. Okay, this is a small dipole, and now we have a PEC. So it will mirror, and if we have to remove this PEC, what we do is we take mirror of the charges. So we have, for the minus we get plus over here, and for the plus we get minus over here. This, if this acts like a mirror, this is and the dipole's direction is given in this direction, right? So similarly, if we have this monopole over here, if we remove this PEC, we end up with this whole structure over here. So there is a feed over here, and then there is this. Now this becomes a half dipole radiating in, but we have to note that it is radiating only into the upper half. Although we removed this PEC to solve our problem, and do the derivations, but we have to remember that this is still PEC. So there are no radiations in this direction. It will only radiate in this in on the above the PEC. Now, once we have changed this figure to this figure, we can use all the expressions that we derived in the previous slides, um, and similar, and we can directly use the pattern function that we had done for um, the half dipole, and this. Sorry about that. Um, we can use this pattern function, but make sure that we draw the pattern function only on the upper half of the PC. So we've got the radiation pattern. We've got the expression for the pattern now. So the first thing is done. We have got the radiation pattern. Now we need to find the radiation resistance. So now the Pointing vector average only holds true for 0 to pi by 2. So only in the upper half. In the lower half, we have no radiation, as this is a monopole. So the radiated power, which was 36.54, we have to make it half by 2. So we get the half radiated power, and radiation resistance also becomes half from 75, sorry, 71, it was some 71 something value, right? So anyways, this we substitute this p r over here, and we get 36.54. So we did radiation pattern, we have done radiation resistance. Now we are left with directivity. So to calculate the directivity, we know that although the maximum radiation intensity remains same, as you can see in the half, this is maximum 1, but the average radiation intensity now is PR by 2 pi. Okay, so so this is, yeah, so the average radiation intensity is, earlier it was PR over pi, right? And now it is PR over 2 pi. So taking that, we end up with the derivative is 1.64, which is same as the directivity of a half wave antenna. So that was it. You can go over this example. This example is again from the textbook, DK Cheng. Maybe I'll share share the first assignment 1 also in this week. Um, the assignment will be mostly questions from the DK Cheng book. It's selected questions. I'm not sure if I'll be sharing the solutions, maybe if I have time, but you need not return the assignments. They are meant for self-practice. So we are done with the half-wave dipole. Now within this topics, there is something called as effective antenna length, which is very kind of very important to know, because even if you have an antenna of particular length L, it does not mean that uh, if you calculate, and if you say we are working at a certain frequency, a certain wavelength lambda, it does not mean that every antenna which is of this length will always uh, radiate at the same frequency. For example, it is this possible that you have an antenna which is of length L1, which works at a frequency lambda, versus a frequency F1, and then there is another antenna which is also at length L1, but it radiates at frequency F2, because both of them do not have the same this effective length. So they could have different effective length, and hence different frequency of operation. So you must have everybody from the antenna engineering background might have seen papers claiming that they have reduced the antenna size. They have reduced the antenna size, and they're still achieving the same frequency. So what they are doing is they're reducing the length, but even after reducing the length, they are maintaining the effective length. Okay, so a very popular example is you could have a dipole which is of this length, particular length L, like, and then you could have a meandered antenna. So its total length would be will be smaller than the this length L. Or if you are going through all like if you taking the entire length as well, so this particular length, which is the meandered length, L meandered, could be greater than the L1, but both of them would be radiated the same frequency because they would have the L effective same. I I'm if do you have any questions on this? Was I able to make it clear that two antennas, A1 and A2, can have physical length L1 and L2, can but and radiate at the same frequency F1 because they have the same effective length. So this physical length might be different, but the same effective length. But similarly, they could be two antennas A3 and A4. They might have same length, physical length LP, but they might radiate at frequency F3 and F4 because they have different effective lengths L3 and L4. Okay, so we'll proceed with the effective antenna length. So basically, the gist has been like I've tried to convey the gist of what the antenna effective length is. We'll look at some math, but the idea is more important, that an antenna could have a physical length of very large physical length, but its effective length could be much less, or it could be physically very small, but its effective length would be much larger. And we have to know that the frequency of operation, or the radiation frequency, or where the antenna would work is dependent upon the effective length of the antenna, or not the physical length. But usually there is a correlation between the physical length and the effective length. Okay, so we'll discuss it over uh, a dipole itself. So there is another question by Hanuman. I think it's there in the uh, Q&A. Once the lengths are same, I don't see there will be any change in the effective lengths. There is to answer that, there is change. Um, so to to this might be confusing, but you must know about patch antennas, right? Okay, so there is some cut over here for a bit is matching. They look like this, and then there is a dipole which looks like this. So over here you can see the physical length, which is almost equal to, like, very close to effective length. Over here also, this is this its physical length will not be equal to the effective length also. We'll see that. And what is the length over here? Okay, so like, how do you like quantify the physical length of the antenna for an antenna which is not a dipole antenna? Uh, so over here, this could be some physical length, but it is definitely not equal to the effective length. So so essentially, this is what I'm trying to say. So the effective length is the parameter which determines the frequency of operation, the frequency at which it will receive or radiate, and not the physical length. Um, yeah. So I think if you okay, so if yeah, if you since okay, so the cases are different because this is dipole versus patch. But what I'm trying to say is there are different antennas. For example, there is Vivaldi antennas, there are bow tie antennas. So all of them will have certain effective lengths. So that is the important factor. And so you're saying that, okay, your question was, there are two antennas and they have the same length, how is the physical length different? So what I was trying to say is based on the geometry. So if you curve an antenna, and if there is a straight antenna, the frequency of operation will change. Although there is a physical length, this is the physical length, but and this is one of the dimension in which the curve is there, but the frequency of radiation will depend upon a length which might be in between these two lengths. So there's a physical length, and then there is another total length, for example, if you said lt, but again the radiation will be the effective length you'll find out will lie in between these two. So based on how for meandered line, as I told in the previous example, if you use a meandered line, and if you calculate the length from here, and you by using a string or something, if you calculate this length, it will turn out to be some meandered length, but it will not be same as its radiation frequency will not be same as a dipole if you which has the same this lm length. Both of them will have some difference in the frequency of radiation. So which is due to the effective length, how much of uh, the length of the antenna is actually affecting so again, like the radiation resistance, the effective length is also a fictitious value. It doesn't really exist in the physical sense, but we are giving it a we're we're calculating and giving one parameter that lets us determine where the frequency of operation would be. Okay. Okay. I get it that it's not very intuitive at first, but let's do the derivation and then see. So just okay. So one of the things which I think missed to say, that this effective length is actually dependent upon the current distribution of how the current is distributed over the antenna, and due to the current distribution. Um, uh, Due to the current distribution, the effective length of the antenna would change, and this current distribution is also dependent upon how you design the physical like structure of the antenna. So for a different physical structures, the current distribution on this the structure would be different, and hence the effective length would be different. Is what I'm trying to say. So what like maybe I'll write it over here. Different structure means different current distribution, and different current distribution means different effective length. This is what I'm trying to say. Okay. So we'll go through this one example of for a linear dipole, and then try to generalize. Okay. So the electric field in the far field zone for the thin wire dipole that we discussed in the beginning of the class is given us by this expression, and then for the far field, uh, uh, it can be approximated like yeah, and so we also yeah. So over here, we had some distribution as Im and the sine beta, this distribution, and yeah. So essentially, this was the expression, right? We had this Iz, and this Iz was substitute. This was okay. So this arrow should have been like this. So we had this expression for uh, the electric field, where this electric field which we have is dependent upon the current distribution, this I said. So we in one of the cases for the thin wire dipole, we used, if you remember, current is equals to some sine beta. We had this expression written like this, right? Sine beta and stuff. And for greater than z and less than z, we had expression. So if you remember that expression, so we had the expression for electric field, which is dependent upon the current distribution. Now, we could have the input current at the I0 as the input current at the feed point, and let us assume that this current distribution remains same throughout the dipole. So we will okay. If we take equal current distribution I0 over here, this will come out of the expression at the port, and then we have the effective length, which summarizes this. So the effective length is given by this expression for small antennas as sine theta upon I naught integral of minus h to h from like the physic from starting to end of the physical dimension, and how the current is distributed over it. So this is the definition of the effective length. So we had the expression for electric field, and within that um, we substituted Iz as I with I0 and LE over here, and this LE is defined by this expression. So if we substitute by this back over here, we'll get the same expression. So we have defined the electrical the effective length now. Now with so we started with the expression for we had the expression for the for thin wire dipole, and this was from the and the electric field dependent upon was dependent upon the current distribution, and the current distribution could be like we can separate this out from this expression by using the term effective length. And this effective length is given by this expression over here. Now, from this expression, the at the effective length, the LE measures the effectiveness of an antenna as a radiator, and for a given current distribution, the far zone field is proportional to LE. So this LE, as you see, which is over here, determines how the electric field would look like in the far field. So you must remember that this expression that these expressions for electric field that we're talking about are the ones in the far field that we chose. We have ignored the 1 by r square and 1 by r cube terms. So all the discussion is for the far field, and based on and this electric field is now depend is a function of this expression which we are calling as effective length, and this effective length is a function of the current distribution. So this current distribution will affect the electric field, and this particular current distribution also contains information about the directional properties of the antenna. So if this current distribution changes, the the radiation properties will also change. And in most practical situations, the important value of the effective length is that at theta equal to pi by 2. So if you remember, when we plotted the radiation pattern, right? So the radiation pattern for the half dipole antenna look like this. So over here we had uh, the maximum radiation at theta equal to pi by 2, and this is the value which we usually take. For most cases, it is theta equal to pi by 2, and if you put pi by 2 over here, this cos term becomes 0, and this e power entire thing becomes 1. So we have L equals to 1 upon I naught minus the integral from minus h to h over the physical dimension and the current distribution. So L effective is essentially some function of the current distribution over the physical length of the antenna. So from this expression, it indicates that this effective length is a length equal to a linear antenna with a uniform current I naught such that it radiates the same far field zone as pi by 2. Um, what we're trying to say uh, is the this LE gives the length of the antenna such that so this particular dipole is radiating some E field in the far field, right? In the far field, we are getting some electric field value, and there could be another and for this dipole antenna, the electric field distribution, sorry, the current distribution looks like this, which is some sort of sinusoidal distribution. Uh, but there could be there could be a current distribution which was like equal current throughout the dipole, and this dipole would radiate some uh, this would radiate the same electric field values. Same We'll get the same electric field expression from an antenna whose current distribution throughout was same, instead of being zero at the corners and increasing towards the field. If it was constant throughout, there could be another antenna. I will get the same electric field expression. So if for this antenna, which would have the equal current distribution throughout and will give the same expression for electric field, is the its length is the effective antenna length. So there is a question from Amina. Yes, Amina. Is your question in the chat or the Q&A? I don't see your question written. Um, if you want to unmute yourself and ask, please go ahead. Or if you want to type in your question, that's also fine.
Sir, nothing, sir. Nothing, sir.
Oh, okay. Oh, well, maybe you can put your hand down. Okay. So this is what we're trying to say, that there is this antenna whose current distribution looks like this, like a bow, and there could be another antenna whose current distribution would be like equal current throughout the antenna. Both of them would have certain length, this certain lengths, and they are radiating the same electric field in the far field. So the antenna with the constant current distribution, the equal current throughout the antenna, that length is actually the effective length. I hope that made sense. Maybe we'll cover the material on the effective antenna length, this example, and then we can pause to take questions, and maybe if Hanuman has further questions, we can discuss that as well. So we are to assume a sinusoidal current distribution on a center-fed thin straight half wave dipole. Okay, so there is a center-fed thin half wave dipole, one which we are looking at in the last few slides. We have to find its effective length and what is its maximum value. So from the previous discussions, we have this information. We have so this is the how the current will be distributed along the antenna, a sinusoidal current distribution. And we, in the previous slide, we had derived the expression for the effective length. And this is the current distribution, which can be substituted over here. Okay, so let's do that. So we're given the length. So this is a half wave dipole, right? So we had 2h equals lambda by 2, which implies h equal to lambda by 4. We can substitute that. We Over here, the maximum value of I naught is Im at the feed. And similarly, we have, so using this expression and substituting the current distribution inside the expression for effective length, we are getting this expression. So sine beta lambda by 4 minus z e power beta z cos theta. And if you evaluate this integral, uh, uh, this is what we end up with. The effective length would be 2 upon beta cos pi by 2 cos theta and sine upon sine theta. This is the effective length that we have got. So remember that although its physical length is lambda by 4, its effective length turns out to be 2 upon beta cos pi by 2 cos theta upon sine theta. And now, since the maximum value is found out at theta equal to pi by 2, the effective length would be this thing will be 1, and this will be 2 upon beta, and this turns out to be lambda upon pi. So lambda upon pi uh, is, sorry, so h is lambda by 4, and it's effective, so its physical length is lambda by 2 because we have 2h, right? The length of the dipole is h plus h, so which is lambda by 4 plus lambda by 4. So this is lambda by 2. So although the uh, physical length is lambda by 2, its effective length is lambda upon 3.14. So which is smaller. So it turns out, if due to the sinusoidal current distribution on the half-wave dipole, uh, and the half-wave dipole's effective length is not even not half wave, not half the wavelength. It's lambda upon pi. So this is somewhat something was trying to say. Based on the current distribution on the antenna, the effective length could be different because the effective length considers that the current distribution is equal along the dimension, and this is for the dipole antennas. So if you, for example, if you so over here the current distribution looks something like this. This is half wave, right? So and this is half, and this is half, and yeah. So it was something like some sort of semi-circular distribution. And if you had considered a current distribution like this triangular distribution, then the effective length would turn out to be something different. So based on the current distribution, the effective length would change. Okay, and if you upon further examination, like if you look at this, so there could be a case, if so right now we were looking at a half dipole, so where the current distribution was something like this. But if this antenna gets longer, then there would be a current distribution which look something like this, and the current at the feed, and this value I0 will be less than the IM value. So the IM is the maximum current value, right? So IM is the maximum value, and we are to take this I0 value, which is at the feed. So this feed value could be this feed value could be smaller, and this would mean the effective length is greater than the physical length, which is not true, because which is uh, not true because the effective length has to be smaller, because if you had equal current distribution throughout the antenna, then you get the maximum radiation. But if you have something of this pattern, it implies some of the regions, like empirically saying, have lower current values, and hence uh, the effective field values should be lower. So hence we have come up with a different expression for the effective length for antennas whose lengths are comparable to uh, the wavelength of the antenna. For bigger antennas, the we define the effective length differently, and this expression is the voltage at the voltage at the port, um, upon the electric field at in the far field, the electric field expression in the far field. So this is how we are defining the effective length. So this is the new expression. So for smaller antennas, this is the expression, but for bigger antennas, this is the expression. And okay, so that's about it, I think. Yeah, so there is another, so since we are like close to the time. I'll just quickly cover the last few slides and then take questions. So up till now we were looking at the transmitting antennas, and by the theorem of reciprocity, the reciprocity property of the antennas, the effective length of the antenna for receiving will also be same as transmitting. Okay, so sorry, we were looking at the receiving antennas, and by reciprocity we can show that the for the transmitting antennas as well, uh, we have the same expression for the effective length. Um, and in the coming classes we will discuss will shall prove that for both uh, the impedance and the directional pattern. Right now all the discussions were on receiving antennas. For the transmitting also, the impedance and the directional pattern and all the things will be the same. um, okay, and there is one another term called as polarization mismatch over here, which is so in this case, as you so this effective length is one term, and there is electric field. So the voltage which appears at this terminal is essentially it depends upon the orientation of this electric field. So if the electric field is oriented like this, the voltage which is received on this antenna will be maximum. But if the electric field is oriented like this, and the horizontal toward like perpendicular to the antenna, the obtained this voltage at the port will be minimum. So this is due to phenomenon called as polarization mismatch. So based on the electric field orientation, the voltage received at the port changes, and hence this expression, which the effective length, which was this, can be rewritten to accommodate for polarization mismatch as well. So now uh, the scale up, the dot product of the effective length and the incident electric field gives the uh, voltage which is absorbed at the receiving antenna terminal. So the voltage which is received at the antenna terminal is a function of the electric field's orientation, the electric field and its orientation, and the effective length of the antenna. So if the antenna has a higher effective length, it will receive more. The higher will be the potential difference which is observed here, and if the potential difference will also be higher if you are receiving higher magnitude of electric field, or if it is aligned in the current orientation. So this is the expression for the for voltage at the port. Its dependence on the antenna effective length and the orientation of the electric field and its magnitude. So this is what we had to cover in this class. If there are questions, we can take them now. We uh, like sort of are on time. Um, we can pause here, take a few questions, or we can discuss them in the WhatsApp group, or you can email them email the questions to me as well. In the next class, we'll look at antenna arrays, and then we'll start with two element array, and then look at general uniform arrays. Okay, I'll pause here. If there are questions, you can wait, or I'll share the slides at the as we end the class, and upload the recordings as well. So if there are no questions, we'll stop now. I'll stop the recording. Okay. Thanks for joining. See you in the next